Okay, we got a test in 1 week. That's number 3. We've got 6 sections of chapter 5. We covered 1 section of chapter 6. I plan to cover the other 2 today. We'll see what you guys decide on the last 2 sections, whether you want them on this test or just wait for the final exam for those. I'll let you guys decide maybe. And I've already got web work up for those 3 sections. What's the matter?
You're early.
I'm early? I gotta set up my toys. I gotta talk to my people. I gotta get your pulse. How is your trig going now that we're almost finished with the semester? Is it everything you hoped for and more? That's why you're sitting there. I'll be glad to take your questions. Are we still lingering around on chapter 5 homework? Yes? You just enjoying chapter 5 so much you refuse to get out of there? Well, there's the truth right there. I opened them all again. This is a lot of whiners. I listen to the whiners. Yes, ma'am. Okay. Do you have it on you or am I pulling it up? All right, fire when ready. And I'm sorry, I missed the numerator of what the cosine t was given as. So, -7/8. Okay, so given the cosine, we can find those other trig functions because we have identities that write our trig functions in terms of a single angle A. And if you know, or single angle T in this example, and if you know the value of one trig function at that angle T, you know them all. This is telling us right here that angle T is between pi and 3 pi over 2. That puts angle T in quadrant 3. So I can draw a quadrant 3 angle that shows that the adjacent side divided by the hypotenuse is -7/8. The adjacent side would be the -7. The hypotenuse is always positive. Then we'll do the Pythagorean theorem to find the negative value for the y. And you have that y squared plus -7 squared is 8 squared. So y squared plus 49 is 64. Subtract 49 from 64 might be 15. So y is the square root of 15, and we will take the negative square root since in quadrant 3, the y values are negative. So for the cosine of 2t, my pencil lead, you will have the identities. I know them. Don't you wish you knew them too? But you'll have these identities given for you. There is a cosine identity for the double angle strictly in terms of cosine of the single angle. And it's 2 times cosine squared of the single angle minus 1. And so we've got the cosine of the single angle as -7/8. We'll just fill that in here, square it, multiply by 2, subtract 1, boom, we're done. So 2 times -7/8 squared minus 1. 7/8 squared is 49/64. This is a 2/1. I can divide the 2 into 64 and get 32. And then I can treat the 1 as 32/32. 49 minus 32 is 17. And then over 32. So that's what I'm getting as the cosine of 2t, 17/32. Notice that if t lies between pi and 3π/2, if I go through here and double everything, then 2t is between 2π and 3π, 2t. So that says it's in either quadrant 1 or 2. Since it's positive, it's in quadrant 1. The identity for the sine of 2t is 2 sine t cosine t. We can get the sine of t by looking at the opposite over the hypotenuse. So where I have the sine of t, I'm going to fill in negative square root of 15/8. And then the cosine of t was given as negative 7/8. The negative square root of 15 times the negative 7 gives me a positive 7 square root of 15. 8 times 8 is 64. Again, divide that by 2, and I get 32. 7 square root of 15 divided by 32 is the sine. The two half angle formulas have a plus or minus in front of the square root sign. I'm going to go ahead and figure out what quadrant the half angles are in. So again, I'm going to start with pi is less than t is less than 3π/2. And I'm going to divide everything by 2. So I have pi/2 is less than t/2 is less than 3π/4. So that's in quadrant 2. Quadrant 2 has a negative value for the cosine of t/2, and quadrant 2 has a positive value of the sine. So next, to get the cosine of t/2, we said it was going to be negative, and it's the square root of 1 plus the cosine of the single angle all over 2. And that expression, the entire thing is under the radical sign. We're given the cosine of t. Cosine of t is negative 7/8. So think of this one as being 8/8 plus negative 7/8 is 1/8. Divide 1/8 by 2 and you get 1/16. So negative square root of 1/16. 1/16 is a perfect square because 1/4 times 1/4 is 1/16. So our answer here is a negative 1/4. The sine identity has a minus in between. And we know that the t/2 is in quadrant 2, so we take the positive square root. So for the sine of t divided by 2, we have the positive square root of 1 minus the cosine of t divided by 2. So we fill in that same value of the cosine of t. We have 1 minus a negative 7/8 divided by 2. So let's think of the numerator as being 8/8 plus 7/8. That gives us 15/8. Divide 15/8 by 2 and we get 15/16. The 16 is a perfect square, so I can take it out and write that as 4. But keep the numerator as the square root of 15. Again, it's positive because we are in quadrant 2. So there are 4 values. And that's the game we played over and over and over and over again with our identities. If you want to find the sine, cosine, tangent, whatever trig function of a sum, difference, double, half angle, you spread that out in terms of the identity of the single angle, draw the triangle, fill in the numbers. 5 sections of doing the same thing over and over and over again. We good with that?
On this, if we stop at the square root of -1.
Yeah, you can stop way up here. But you know, sometimes I have to make multiple choice, so you have to be able to get your answer to look like mine. I won't do too much. I wish I didn't have to make multiple choice, but there's too many people. Maybe we'll just take the test and then swap it and you guys grade each other's tests.
Yeah, I like that.
You have to do that? Grading's hard. You would do it honestly, or would you just kind of half-ass it? You would, but then you know the person next to you's grade. That's a FERPA violation. We couldn't do that. So even though you volunteered, it is against the law. You can probably get your kindergarten teacher locked up. Did you? For a grade, you swapped tests and graded each other's? You didn't have to hide the name? Dang, get your college algebra teacher arrested too. Lock her up, lock her. No. Dude, lock him up. That's even better. What else? Let me see if you know what the inverse trig functions are. So a quick review of what we did last time from section 6.1. So section 6.1a, quick review. We defined our inverse trig functions. Y is equal to the inverse sine of x is an angle y that we take the sine of to get the number x. That number x is a number between -1 and 1. And for the sine, that number y was between -π² and +π². So it gives us an angle, an acute angle, either in quadrant 1 or a negative acute angle in quadrant 4, depending on whether the input is a positive or negative number. And you should also be aware that another way to write inverse sine is arc sine. So similar definitions for the inverse cosine. Y is equal to the inverse cosine of a number x if and only if the cosine of this angle y gives you back that number x. The x is the same as above, a number between -1 and 1, because with inverse functions, the domain of the sine and cosine becomes the range of the inverse function, and the range, which is the numbers between -1 and 1, becomes the domain of the inverse functions. So the -1 to 1 are these numbers here, and for the cosine, the values of y have to be between 0 and pi. So if the angle's positive, you give me a quadrant 1 angle. If the angle's negative, you give me that reference angle version in quadrant 2. The inverse tangent has the same description for the output values as the inverse sine, except for it's an open interval. Y is equal to the inverse tangent of x if and only if the tangent of y gives me back x. In this case, the x's can be any real number, but the y values have to be strictly between -π² and +π². If you ever want to deal with other inverse trig functions, you can convert them to these with the identities that the inverse cosecant of x is the same as the inverse sine of 1 over x. The inverse secant of x is the same as the inverse cosine of 1 over x and the inverse cotangent of a number is the same as the inverse tangent of 1 over that number. So if you use these, then you'll only have to remember the domains and ranges of the trig functions above. So for instance, we can find each of the following. Find exact values of, number 1, the inverse sine of negative square root of 2 over 2 added to the inverse cosine of negative square root of 2 over 2. So I'm asking you to find two angles here and then add them together. What acute angle do we take the sine of to get a negative square root of 2 over 2? It'd be, I'm in radians here with our inverse trig functions. So 45 degrees, it's got to be negative, so it's going to be a negative 45 degrees. These inverse trig functions are in radians, so this would be a negative pi over 4. But the cosine, if it's a negative number, is the angle in quadrant 2 that we would take the cosine of to get square root of 2 over 2. So what's the quadrant 2 version? And give me in radians, please. 3 pi over 4, add a baby. And now we add those two together and we get 2 pi over 4, which is pi halves. All right, my second one here. Suppose I want to find the inverse cosecant of just the square root of 2. Then what we do is we write that as the inverse sine of 1 over the square root of 2. And then I hope you recognize that 1 over square root of 2 is the same as square root of 2 over 2. So we're back at that 45-degree angle. This time we're in quadrant 1. So in radians, our angle is pi over 4. Okay, then how about if it's not an angle that we know? Suppose I want to find a composite function. Maybe I want to find the tangent of the arc cosine of negative 3/5. The arc cosine of negative 3/5 is an angle in quadrant 2 because it's negative, and that's the range of the arc cosine. A quadrant 2 angle that I would take the cosine of to get negative 3/5. That's not one of the angles that I know out of my reference angles, but if I know I'm taking the cosine of an angle to get negative 3/5, I should be able to find the values of all trig functions of that angle, in particular the tangent of that angle. So I start by saying the stuff in the parentheses is just another way to write an angle. So I'm going to say let A be the arc cosine of negative 3/5. And by our definition, that means the cosine of that angle A is minus 3 over 5. And my job now is to find the tangent of that angle A. Knowing the cosine will tell me the values of all 6 trig functions. Just draw your quadrant 2 triangle. Quadrant 2 goes back in the X, up in the Y. The adjacent side will be the negative 3. The hypotenuse will be 5. what's the opposite side going to be? And it will be a positive 4 because y is positive in quadrant 2. And now looking at that picture, I can see the tangent of that angle is 4 divided by -3. Okay. We can also use identities here. Let's look at one very similar. Suppose I want to find the cosine of 2 times the inverse sine of 1/4. The inverse trig function itself is an angle. It's an angle that I would take the sine of to get 1/4. So again, it's not an angle that I have memorized. But I can do the same kind of stuff. I can just pull this piece out and substitute it in for whatever I want to use as my angle. So I'll use A. And I know that A is an angle that I take the sine of to get 1/4. And so when I put an A right here, my objective in this problem is to find the cosine of 2 times A. And I know from chapter 5 that I can find the cosine of twice an angle using an identity. One identity that comes to mind is the cosine of twice an angle is 1 minus 2 times the sine squared of the single angle. I don't have to draw a triangle because I already know what the sine of that single angle is. That's 1/4. So I'm going to put it here, square it, multiply by 2, subtract that from 1, and I'll have the cosine of 2A. So I have 1 minus 2 times 1/4 all squared. 1/4 squared is 1/16. Times 2 is 2/16 or 1/8. 1 minus 1/8 is 7/8. Okay. Let's do the same thing with an addition formula. Probably don't have room right there. Let's go to the next page. Let's find the tangent of the inverse sine of 3/5 plus the inverse cosine of 5/13. Just get in your head, inverse trig functions represent angles. Inverse trig functions are angles. I'm trying to find the tangent of the sum of 2 angles. So grab you 2 variables and represent those angles with those variables. I'm going to say A is the inverse sine of 3/5. B is the inverse cosine of 5/13. And I'm going to look for the tangent of A plus B. I'm going to take A to be the inverse sine of 3/5, which means the sine of A is 3/5. I'm going to take B to be the inverse cosine of 5/13, which means the cosine of angle B gives me 5/13. Those are all positive numbers, so both of these have to be in quadrant 1. I'm going to draw those 2 triangles because I'm going to need to find the tangent of them. I'll need the other sides. So here's angle A. The sine of angle A is opposite over hypotenuse. So the opposite is 3, the hypotenuse is 5. That's the ever popular 3, 4, 5 triangle. Angle B in a triangle will give me this picture. I know the cosine of B is adjacent over hypotenuse. So I got the 5 right here and the 13 here. If you do the Pythagorean theorem, you'll see that that side is 12. Those are the two triangles that I remember the most, the 3, 4, 5 and the 5, 12, 13. You know, when you're doing these, make sure that you check that the longest side of your triangle is the hypotenuse. Some of you are asking questions, why am I not getting this right? You're just putting the numbers on the wrong parts. So if you quickly eyeball it, make sure the biggest number is on the hypotenuse, you're probably going in the right direction. Okay, now I got to use the identity for the tangent of A plus B. And like I said, you'll be given these. I know them. I didn't always know them. I have to stand up here and talk about them. So maybe if you're into memorizing things, you're welcome to come up here and just recite them. You know, that Squid Game version. Tangent of A plus B is tangent of A plus the tangent of B divided by 1 minus tangent of A times the tangent of B. I look at triangle A and I see the tangent of angle A is 3/4. Opposite over adjacent. From the triangle with angle B in it, the tangent of angle B is 12 divided by 5. So when I put all that stuff in, I get this. I'm going to go ahead and simplify that just to show you how it's done. To add two fractions, you need a common denominator. The common denominator between 4 and 5 is 20. So I can write 3/4 as 15/20. And I can write 12/5 as 48/20. I don't need a common denominator to multiply. To multiply, I can just multiply straight across. So I have 1 minus 36/20. (15 plus 48, 63/20. Think of this one as 20/20. 20/20 minus 36/20 is a negative 16/20. And when you flip and multiply, you can see that the 20s cancel, and you end up with a negative 63/16. There are times in your calculus class that you're going to need to find these composite functions without using any numbers. So let me take the numbers out and do the same thing in terms of a variable. So for example, my next example, write the following. As an algebraic function of the variable u. So get the trig out of here. Let's see, let's take the sine of 2 times the inverse secant of u. The presence of the 2 there means I've got to use a double angle formula. So let's call this part A. And I'm going to find the sine of 2 times A, but I want to write it only in terms of u, no trig functions in it. If the inverse secant of u is A, then I know that the secant of angle A has to simplify to u. I'm going to write that as the ratio of two sides of a triangle, so think of it as u divided by 1. And the secant is going to be the hypotenuse divided by the adjacent side. You remember that, right? So here's my triangle with angle A in it. The hypotenuse has length of u, the adjacent side has length 1. I'm going to need this side over here. Let's write y in terms of u using the Pythagorean theorem, that 1 squared plus y squared is u squared. So y squared is u squared minus that 1. That gives me y as the square root of u squared minus 1. Now let's hold off on that picture and go down here and expand the sine of 2 times a using the double angle identity for the sine. It's 2 times the sine of angle A, cosine of angle A. I can get both the sine and cosine looking at the triangle. The sine is opposite over hypotenuse. So I got that square root thing divided by the u squared minus 1 divided by u. And the cosine of angle A is adjacent over the hypotenuse. So my final answer is an algebraic expression. There are no trig functions in it. Just multiply straight across. 2 times the square root of u squared minus 1 divided by u squared. Anybody follow any of the stuff that we're doing right here? Not at all, because you haven't tried any of the work. Haven't tried any of the homework since Tuesday. We spent Tuesday night and Wednesday night just goofing off. Oh, those other classes. The main point is inverse trig functions find us some angles. We are going to look at solving trig equations today, and the equations will probably have angles as the solutions that we know and love, our reference angles. But if it's not an angle that we know and love, we'll write it in terms of an inverse trig function. And then if we had to have a number, we've got a calculator that have those inverse trig functions on them. Your calculator will have to be put in either radians or degrees, depending on the question. So for instance, if you have some sort of expression like this, so in degrees, let's see if we can find the x for which the sine of x degrees is equal to 3/4. I could draw a triangle and show you what a triangle looks like, but I don't want the triangle. I want the measure of the angle. To get the measure of the angle, I recognize that 3/4 is not one of the numbers that I know. 0, square root of 2 over 2, 1/2, square root of 3 over 2, 1. This is not one of the ones I know. So the best I can do right off the bat is to say that that angle x is the inverse sine of 3/4. And then I get out the calculator that I don't have and see if I can compute that. Let me see if I can find it on here. Calculator, I'm going to put it in degrees. And I'm going to take the inverse sine of 3/4. And it says it's about 48.6 degrees. Okay. Calculators are nothing exciting. Let's get out of here and go back to my, see if I can get out of here. I want to go back to my flex cam. Get back here, flex cam. Okay, well, find it. Where'd it go? There it is. All right, so we're back. Okay, so that's what we're going to do today. Solve equations. If we don't know the angle, we can use an inverse trig function. You ready to go at it? For some reason, this textbook put the topic of solving trig equations in 2 sections. We don't need to do it in 2 sections. We'll do it in 1 section. So I'm going to label my notes now as sections 6.2 and 6.3, solving trig equations. Okay, so I'm going to give you some mini trig equations that you can solve based upon your knowledge of the unit circle. We've been doing these all semester. We're going to do it again. I want you to give me the solutions in 2 different ways. I want you to give me the solutions in the interval from 0 to 2 pi, so using radian measure, and then give me the solutions in the interval from 0 degrees to 360 degrees. So here's my first equation. Sine of what x is 1? Give me an x in the interval from 0 to 2 pi that I take the sine of. Sine of in 0 to 2 pi. Thank you. And then in 0 to 360, it would be 90 degrees. And that's the only one, right? Now give me all angles in which the tangent of x is equal to -1. In radians first. Tangent is negative in quadrants 2 and 4. Swatch of the pi. Not over 2. If tangent's going to be 1, then the sine and cosine are the same, and that occurs at pi over 4. So in quadrant 2, the pi over 4 is 3 pi over 4. And in quadrant 4, it's 7 pi over 4, because I'm treating 2 pi as 8 pi over 4. So back up 1 pi over 4, and you're at 7 pi over 4. All right, you degree lovers. What's the comparable 45-degree angle in quadrant 2? 135, just take 180 minus 45. And then to get the quadrant 4, take 360 minus 45. 315. All right, let's do another one. Let's do cosine of x is equal to 2. Any solutions to the equation cosine of x is equal to 2? Sorry? No, cosine of 0 is 1. Trick question. When is the cosine ever bigger than 1? Never, right? There are no solutions to this equation. Okay, we are going to try to get terms in our equations that are as easy as that. If we can get our trig function by itself and a number on the other side, if it's one of the numbers in our table, spit it out. If it's not, we can use an inverse trig function. So for instance, here's a trig equation. How about the same equation as number 2, but I'm going to change it up a little bit. Tangent squared of x is equal to positive 1. Well, if you were solving the equation x squared is equal to 16, you would take square roots of both sides and get x is plus and minus 4. We're going to do that here. The tangent squared of an angle is equal to a number if and only if the tangent of that number is plus or minus the square root of 1. Well, the square root of 1 is just 1. Earlier, you gave me the 2 radian measures at which the tangent is -1. So we have to throw into that list the 2 other angles at which the tangent is +1, namely pi over 4 and 5 pi over 4. So the solutions here in radian measure is pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. In terms of degrees, we got the 45 degrees. 3 pi over 4 is 180 minus 45 degrees is 135. And then 5 pi over 4 is 180 plus 45 degrees, or 225. And then there's the 315 degrees that we got earlier. So these types of trig equations are going to fall into the category of know your unit circle. In both radians and degrees. The next type of trig equation I want to look at is the solve by factoring type. For instance, if you're solving a second degree equation in the variable x, like x squared plus 4x minus 5 is equal to 0. If you're pretty good at factoring, you know that there are factors of 5, opposite in sign, that add to 4. And you would write this equation then as x plus 5, x minus 1. If you can write a sum as a product, then that product equal to 0 happens only when either factor is 0. So a product is 0 only when either factor is 0. So I get 2 solutions here. X is -5, x is equal to 1. If we have a trig equation and we can possibly factor it, we'll try to do that. And then we'll set each factor equal to 0. So here's one right here. I want to know where the cosine of theta times the tangent of theta minus the cosine of theta is 0. And I want those thetas in the interval in radian measure between 0 and 2 pi. One lap around the unit circle. And the hint is we're going to solve this by factoring. I'm subtracting 2 terms to get 0. And there's a common factor in the 2 terms. There's a common factor of the cosine of theta. So I'm going to write it like this. I'm going to pull out the common factor. We'll take a cosine of theta out of each slot. That leaves me a tangent of theta in the first slot Then the minus sign. If I take that out, I got to put a 1 right here. So notice that if I were to multiply that back out, I get the original equation back. But I now have my difference of two terms written as the product of two terms. And just like up here, the product of two terms is 0 only when either of the two factors are 0. So now we write the equation cosine of theta is 0, or the tangent of theta minus 1 is 0. In one lap around the unit circle, where is the cosine going to be 0? Pi over 2 and 3 pi over 2, correct? So this first factor provides two solutions, pi over 2 and 3 pi over 2. This one's the equation we solved up here several times. Tangent of theta is 1. Tangent is 1 at pi over 4, and then again in quadrant 3 at 5 pi over 4. So that one says theta is pi over 4 and 5 pi over 4. So all four of those numbers are solutions to the original equation. One of our steps in factoring is pull out the greatest common factor. All right, another factoring step is to try to factor it as you would a polynomial. So suppose I want to solve the equation sine squared of x plus the sine of x minus 2 is equal to 0. We're going to try to factor this the way we would a second degree equation. Something squared plus that something minus 2. If I ask you, say, for instance, to factor this, could you do it? Could you find me factors of 2, opposite in sign, that add to 1? Say, yeah, plus 2 minus 1. These two have to multiply to the minus 2. The inside terms have to add to the plus 1. This factor's the same way, but instead of a y, we have a sine of x. So I'm going to factor this like I did there. Sine of x times the sine of x gives me a sine squared. Then factors of 2, opposite in sign, that add to 1. So I would need the plus 2 here and the minus 1 there. So make a quick check that the inside terms give you what you said, a positive 1 sine of x. If you were to multiply that out, you'd have a 2 sine of x, a minus 1 sine of x, added together gives you a positive 1 sine of x. But I got that bad boy factored, so now I just set each factor equal to 0. So I have sine of x plus 2 is 0, and sine of x minus 1 is 0. This one gives me the sine of x is negative 2. Got any thoughts about the sine being equal to a negative 2? Can happen. This number's outside the negative 1 and 1 range. So this is not possible. Our solutions will only come from this second factor, and that's where the sine of x is equal to 1. We did that up here at the top of the page. The sine is 1 only at pi halves. Solve by factoring. If we have too many trig functions in our equation, then maybe we'll solve by using some identities and then factoring. So we might need to use identities to get easier equations to factor. That's okay. We got a boatload of identities. We love using them. So I'm going to go through just some rando equations here. And let's see how many we can get done in the next 30 minutes. Okay, we're trying to find all solutions in the interval from 0 to 2 pi. Maybe to make it easier on you, I'm going to give you the angles so that you can look at them. Here's a little chart that you should have memorized by now. We got a theta, and let me give you theta in radians. 0, pi over 6, pi over 4, pi over 3, pi over 2. Then the sine of that angle, then the cosine of that angle, and I'm even going to add a column for tangent to help us answer the first question. Sine of 0 is 0, cosine of 0 is 1, tangent is sine over cosine, so that's 0 divided by 1. Sine of pi 6 is a half, cosine of pi 6 is square root of 3 over 2, tangent is 1/2 divided by square root of 3 over 2. The halves cancel and give you 1 over the square root of 3, which when rationalized is the square root of 3 over 3. Sine and cosine of pi fourths is square root of 2 over 2. Tangent is sine over cosine, so it's going to reduce to 1. Sine of pi thirds is square root of 3 over 2. Cosine is a half. Sine over cosine simplifies to square root of 3. Sine of pi halves is 1. Cosine of pi halves is 0. 1 divided by 0 is not defined. If you need to know these in degrees, this corresponds to 0 degrees, 30 degrees, 45 degrees, 60 degrees, 90 degrees. If you know these, you can get the ones in other quadrants just by adding or subtracting those reference angles from 360 or 2 pi, or 180 or pi, depending on whether you want things in radians or degrees. In this entire worksheet, we're doing things in radians. Okay, we did one like this. We did it where I had a 1. If you've got a second degree equation with a trig function, get the trig function on one side, the number on the other, and solve by taking square roots. So we would write this as the tangent squared of theta is equal to 3. And then I said we're going to solve by taking square roots. Square roots plural. There are 2 numbers you can square to get 3, plus or minus the square root of 3. So the tangent of theta is got to be equal to plus or minus the square root of 3. Right here is where the tangent is square root of 3. There's our reference angle. Now let's just generate all 4 solutions around the unit circle. Pi over 3 is 1 solution in quadrant 1. Think of pi as it being 3 pi over 3. So if you subtract pi over 3, the other one is 2 pi over 3. Then add pi over 3, gives you 4 pi over 3. By golly, 3, give me a 3. And the next one's 5 pi over 3. Solve by taking square roots is one approach. Good. We've done some version of the problem too. When you see a second degree equation and a first degree term, I want you always to get 0 on one side first. We're going to try to solve this second degree equation by factoring. That only applies if you get 0 on one side. So I'm going to add sine of theta and subtract 2. We did that one just mere seconds ago. That factors the way we factored y squared plus y minus 2. We factored the sine squared as a sine of theta times the sine of theta. We factor the 2 as a 2 times 1. I need opposite signs with a 1 in the middle, so I get a +2 and a -1. Then you set each factor equal to 0 and solve for the trig function. The first factor, when I rewrite it, says the sine of theta is -2. Anytime you get a right-hand side outside 1 and -1 for a sine or cosine, just want you to realize that that's not possible. But the sine of theta is 1. Look up here in our table. The sine of theta is 1 at pi/2. And that's the only place that it's a positive 1. So that's the only solution. At 3 pi/2, the sine is a -1. Okay. Just wanted to show you if the problem didn't have a 0 on one side, get the 0 first. The factoring idea only applies with 0 on one side. Multiply two numbers together, the only time there's 0 is if one or the other is 0. But for instance, if you didn't have a 0 and I multiply two numbers together and say get 4, well, that doesn't mean each factor is 4. Each factor could be 2. One could be the square root of 3. The other one would be 4 over the square root of 3. It only applies if the right-hand side is 0. When I see the next one, I've got cosines and sines mixed up. I'm not going to be able to factor that. I can factor second degree sine equations with a middle term of sine, or second degree cosine equations with a first degree cosine. But if I got a second degree cosine and a first degree sine, I can't factor that. But this is where our trig identities come in. I know that I can get rid of a cosine squared and write it in terms of a sine squared. What's the identity I'm thinking of? Pythagorean Theorem. Cosine squared is the same as 1 minus sine squared. So we want to get this out. We want the same trig function. Our goal is to get the same trig function or the same angle or both. So let's replace that with 1 minus sine squared. And then we're going to see if we can factor it after I simplify for a bit. So I'm going to have 2 times 1 minus the sine squared of theta plus 3 times the sine of theta minus 2 is equal to 0. I'm going to distribute the 2 through the first parentheses. 2 minus 2 sine squared theta plus 3 sine theta minus 2 is 0. I see that plus 2 in the front and a minus 2 in the end. Those are going to add each other out. So only 2 terms are left. A minus 2 sine squared theta plus 3 sine of theta. So I've got 2 terms. Then my strategy is to pull out the greatest common factor. They both have a sine. I'm going to pull out the common factor of sine. I take one of the signs out of here. I've got the -2 left, and I've got another sign right there. If I pull the sign out of here, I get +3 left. Factoring, pull out common factors, so that if I were to multiply this back out, I get that line back. But now I got a product. Two things multiplied together to give me 0 can only happen when either of the terms are 0. So now I write sine of theta is 0. And -2 sine theta plus 3 is 0. Sine of theta is 0 at 0, and then again at pi. Then again at 2 pi, but I left an open interval at 2 pi. So I only need the solutions from 0 and pi. This one, theta is 0 or pi. The next one, I'll get the trig function by itself. First, I'll subtract 3, and then I'll divide by -2. So I need to know where the sine of theta is equal to 3/2. What are your thoughts on that? Undefined, right? 3/2 is bigger than 1. Can't happen. That's not possible. So these are our only two solutions. Okay? You can always check your answers. If you put these back into the original equation, it should make a true statement. How's your factoring? That could be trouble. Let's see. Hey, look, there's more on back. Why don't we do more? Number 4. Secant squared of theta times the tangent of theta is equal to 2 theta. One thing I want to warn you about is when you see a theta on both sides, you can't just divide both sides by theta. Because when you do that, you're throwing away half of your solutions. And you also can't do that for all the values of x at which the tangent is 0. So instead of just dividing both sides by a tangent and trying to get rid of that tangent on the right side, get a 0 on one side first. Subtract that from both sides. So write this as secant squared of theta times the tangent of theta minus 2 tan theta is 0. Get a 0 on one side first. Then try to solve by factoring. See, that tangent is a common factor. Pull that common factor out front. And you're left with a secant squared theta from here and a minus 2 from the second term. And set each factor equal to 0. The first one gives me the equation tan theta is 0. The second one says secant squared theta minus 2 is 0. Tangent is 0 everywhere the sine is 0. Because tangent is sine over cosine. Sine is 0 where? Zero and pi. Right? We just did that one. Sine is 0, 0, 0 and pi. This second equation, we've got a second degree trig function without a first degree one. So we're going to try to solve that by taking square roots. So I'll move that 2 over. Then I'll take square roots of both sides. If you don't know where that occurs, the secant is 1 over the cosine. And so if I flip both sides, that's where the cosine theta is 1 over plus or minus the square root of 2. If you rationalize that, that becomes square root of 2 over 2. The sine and cosine are both square root of 2 over 2. along the lines y is equal to x and y is negative x. That's at pi fourths, 3 pi fourths, 5 pi fourths, 7 pi fourths. So we get 4 solutions for that equation. So this entire equation has all 6 of these numbers as the solutions. All good? All right, here's a multiple angle equation. One trig function, and I've already got a 0 over here. So I can kind of look at that and tell you what the answers are. I know what I take the cosine of to get 0. Cosine of what number is 0? Give me a for instance. Pi halves. Cosine of pi halves is 0. Cosine of 3 pi halves is 0. But if this is a multiple angle, remember what that does to the graph. It takes a graph from a period of 2 pi and does it 4 times within there. So I'm going to have 8 solutions to this equation. We're told that theta is between 0 and 2 pi. So if I multiply this by 4, then 4 times 0 is less than or equal to 4 times theta is less than 8 pi. I'm going to give all solutions for 4 theta between 0 and 8 pi. Firstly, between 0 and 2 pi were the 2 numbers I said. Pi halves, 3 pi halves. Now I'm going to go again. Right? I've gotten, that's between 0 and 2 pi. So that's pi halves, that's 3 pi halves. If I add pi to that, I'm back up here. Whoops. Pi plus 3 pi halves gives me 5 pi halves. And plus another pi halves gives me 7 pi halves. So that's between 0 and 2 pi. This is between 0 and 2 pi. This is between 2 pi and 4 pi. So now I got to go between 4 pi and 6 pi. So again, I'm adding pi to each of these numbers, or 2 over 2 pi. So 7 pi halves plus 2 over 2 gives me 9 pi halves, plus 2 over 2 gives me 11 pi halves. And I've got one more lap around the circle. I got to go between 6 pi and 8 pi. So I have that 4 theta is 11, 12, 13 pi over 2, plus 2 more is 15 pi over 2. Those are all values of the angle 4 theta that give me solutions to this equation. But my job is to find angle theta. So I'm going to take these 4 equations and divide both sides by 4. So up here, that'll give me theta is equal to pi over 8 and 3 pi over 8. Divide those by 4. The denominators become 8. 5 pi over 8, 7 pi over 8. Divide by 4, I get 9 pi over 8, 11 pi over 8. And down here, I'll have 13 pi over 8 and 15 pi over 8. So for these multiple angle problems, you first solve for the multiple angle, then divide out the number that's in front. And notice that all of these angles are between 0 and 2 pi. That's if you just have one trig function all by itself of a multiple angle. In my next example, I've got a sine of angle theta and a sine of angle 2 theta. I don't like to mix my angles up in one equation. I'd like them all to be in terms of the same angle. I'd like them all to be in terms of the same trig function if possible. So I'm going to use an identity for the sine of 2 theta. I know I can write that in terms of angle theta. So I'm going to use an identity. The sine of 2 theta looks like 2 times the sine of theta times the cosine of theta. Now I've got things more like I like them. I'm going to get a 0 on one side. I'm going to subtract that mess over. Getting a 0 on one side is one of my basic steps because I'm going to try to solve by factoring. This is an example of an equation that has two terms with a common factor. And we're going to pull the common factor out. I'm going to pull a sine of theta out of each term. Put it out front. I'm pulling it out of here. There's a 1 left behind. When I pull it out of the second term, there's a -2 cosine theta. Now I've got it factored. So let's set each factor equal to 0 and solve for theta. We've done that first equation many, many times. Quick, sine of what angles are 0? 0 and pi. 0 and pi. Somebody said it. The rest of you are just thinking it? Okay, for the next one, I'm going to solve for the trig function. So I'm going to move the -2 cosine theta to the other side. Then I'm going to divide by 2. And I know where the cosine of theta is a half. To make it easier on you, I'm going to show you. Cosine of theta is a half at pi thirds. But you know, cosine's also positive in quadrant 4. So using pi thirds as your reference angle, which pi thirds is in quadrant 4? Pi thirds is correct. There you go. You got them all. Factoring is one of the key steps in solving these trig equations. You got to practice your factoring. The examples I've given you were factoring with a common factor, pull it out, or factoring as you would a second degree equation. All right, I'm gonna do one more with you. I'm gonna use all my time. Because as our new football coach says, some version of, I don't have to be here teaching you. I get to be here teaching you. It made me happy to be here teaching you. This one's going to work very much like one of the earlier ones where I had a double angle in the equation and a single angle in the equation. I'm going to try to replace the double angle with one of my double angle formulas. The cosine of twice an angle has 3 versions of it. I'm going to pick the version of it that involves only this trig function. I'm going to use this identity. That the cosine of twice an angle is 2 times cosine squared of the angle minus 1. So I'm going to put that here using the letter theta instead of a. So I'll have 2 cosine squared theta minus 1 as that slot, plus cosine of theta is 0. I'm going to put this in descending order to see if I can factor it. So I'm going to swap places with the -1 and the cosine of theta. Write it as 2 cosine squared plus cosine -1 is 0. So I know to get the cosine squared, my first slot has to have a cosine times a cosine, but I also have to get a 2. So I got to put that 2 somewhere. Let's put it right here. Now I know the last slots have to be filled by factors of the last number. Well, that's nice. 1 only has factors of 1 and 1. But those numbers have to have an opposite sign and multiply in such a way to give me a +1 in the middle. So which of these has to have the plus sign and which factor has to have the minus sign? The middle term is going to come from the sum of these. If I need a +1 in the middle, I need the plus to go here. Agree? And then the minus goes here. All right, got it factored. Let's set each factor equal to 0. 2 cosine theta -1 is 0. Cosine theta +1 is 0. This first one says 2 times the cosine of theta is 1. So the cosine of theta is 1/2. Do you need me to flip the paper, or do you know an angle at which the cosine is 1/2? Pi thirds. Pi thirds. You needed me to flip the paper, didn't you? Cosine of pi thirds is 1/2. All right. Cosine is also positive in quadrant 4. So using pi thirds as your reference angle, back up pi thirds from the nearest x axis. 5 pi thirds is right. All right, the next equation, cosine of theta +1 is 0 when cosine of theta is -1. There is only one place on the unit circle where the cosine is -1. Pi. Got him. Got him. All right, how do you feel? Fine? Seen one, seen them all? You want 6263 on exam too, or do you want it on just the final? It should. If I put it on the final, you're going to see it in the same way. So, what's the thought? You think you got time to spend enough time between now and Thursday to master solving trig equations? All right, I'll put it on exam 3. Exam 3 goes through 6.3, and I'll put a review sheet up there. Chapter 5 through 6.3. The final is cumulative.
What would somebody do if they have 2 exams?
So you have Cal 2 and
Cal 1.
Cal 1 in this one.
'Cause I
It's
tried-
supposed to be the lower numbered course that gets the preference,
Okay,
but I can work with you. I can give you your exam at a different day.
okay. Yeah, I'll probably know about that.
Yeah, find a day that you're free
Okay.
and I'll have a test for you.
Okay. Like on the 8th, or can you not do it after anything after the 7th?
Is 7th the last day?
I think so. So I have to do before that.
Yeah, legally,
Yeah,
you
that's fine.
know.
I can do it on that day, probably.
You know, if my thing was shut off and that wasn't recording, maybe I could. I can do whatever you want.
I've got the interview, but I was just gonna say, I feel like as always.
Thank you.